Okay, so for an incompressible material, um, oh, thank you. Uh, okay, for an incompressible material, what's the relationship between CPU and CT? Um, okay, so this is, there's not much to this one. So for an incompressible material, we learned that um,
Is that
you have a different question.
did isn't it this incompressible and ideal gas model?
Maybe the one that's on D2L is an older version. Let me check. Yeah, it is. It is. Um, let me go to D2L. Okay. All right. So you got a liquid. So we're going to treat it as incompressible. It goes from one temperature to another. Its pressure varies um, over this range. It gives the specific volume and the specific heat capacity. What's the change in internal energy? Uh, what's the change in enthalpy? Um, okay. So we know that um, we have this relationship that says C, which is CP, and it's equal to CV. It's equal to D specific internal energy with respect to temperature. Um, and so we have a change in temperature. We want a change in specific internal energy. Well, we want the true internal energy, but if we can calculate the specific, we know the mass, so then we can just multiply to get that. Okay, so we're given the specific heat value. So it's 3.4 in kilojoules. So we can write this as 3, if we're going to do it in SI units, 3.4 times 10 to the third is equal to du, d temperature. And so 3.4 times 10 to the third d temperature is equal to du. And now we can integrate both sides. So this is going to be from state 1 to state 2. And this is going to be from state 1 to state 2. Um, and so the temperature one, this, if you do that integration, you get 3.4 times 10 to the third T, where T is evaluated, so state 1 is 30. You could convert these to Kelvin temperatures, but since this is just going to show up as a difference, we could just use the Celsius temperatures too. So this is from 30 Celsius to 55. And this is equal to U evaluated from U1 to U2. So we can think of this as, so this is 3.4 times 10 to the third times the quantity 55 minus 30. And this one is U2 minus U1, which is what delta little u is. So multiply the left side out and you get that delta little u is equal to 85,000. This is SI units, so this is in joules per kilogram. And now we want not the change in the specific internal energy, we want the change in the extensive internal energy. So the change in the true extensive internal energy is just the mass times the change in the specific, which is 0.2 times 85,000, which is 17,000. And this is in joules. One thing, just kind of an intuitive thing that you might notice, the in our like sort of world of daily experiences, energies for thermal things are very high compared to energies for mechanical things. So like the what's the height of a building that you can think of? What's the height of like a skyscraper? I guess let's call it 10 feet per. So let's say 500 feet. So what's that? 100 meters, 150 meters. A tall building is 150 meters. What's the energy to lift a bowling ball to the top of a tall building? Well, a bowling ball is, say, 7 kilograms. So 7 times what? Yeah, so 1,050 newtons. Sorry, 1,050 joules of energy is required to lift a bowling ball to the top. Like that's a lot of effort to bring a bowling ball to the top of a skyscraper. But when you start talking about thermal energies, I mean, just small amounts of temperature changes are talking about like thousands of joules. Same thing with like electrical energies that we're used to in our daily experience are relatively small compared to thermal ones, which is why like you think of something dumb like a hair dryer shorting out circuits in your house, breaking circuits in your house all the time, or space heaters break circuits, is because to make thermal changes takes a surprising amount of energy.
So to heat a kilogram of water by 1 degree, that's 4,000 joules.
A kilogram of water.
If 1 calorie heats
Oh, yeah.
1 degree and 1 Celsius.
Right. So
4 joules in 1 calorie.
1. Yes, exactly. Right. Anyone have any questions about part A? Part A. Okay, part B, what's the change in the liquid's enthalpy? So we have the change in the internal energy. Remember, so let me think of it this way. So specific enthalpy is specific internal energy plus P times specific volume. And so the change in specific enthalpy is the change in the specific internal energy plus the change in P times V. Since it's incompressible, we can write this as change in specific enthalpy is equal to change in specific internal energy plus, which one of these two comes outside of the change? What? I'm going to assume you said specific volume? Yeah. Okay, yes, good. So specific, because specific volume is constant, so this is just equal to V times the change in the pressure. So now we can write this as, we already figured out that the specific internal energy is 85,000. We're given that the specific volume is 8 times 10 to the minus 4. Minus 4. And then times the change in pressure, which we are given. So it goes from 0.15 megapascals to 0.1. Megapascals means times 10 to the 6th. So this is the later pressure, 0.1 times 10 to the 6 minus 0.15 times 10 to the 6. And so the change in specific enthalpy is 84,960. Enthalpy also has units of energy, so this is in joules per kilogram because it's specific. And then the change in big H, the extensive change in enthalpy, is 0.2 times 84,960. So 16,992. And this is in joules. Are these temperatures higher or lower or about the same as room temperature?
A bit higher.
Yeah, a bit higher, right. Room temperature is about 20. So a bit higher. And then how about the pressures? Are these higher or lower, about the same as atmospheric pressure?
Higher.
About the same, I guess, because it's so, but.
Yeah, because 1 bar is equal to 0.1 megapascal.
Exactly, 0.101 megapascals would be atmospheric pressure. So right in that same ballpark, but a little higher in the starting case.
Would it be noticeable if you were like 0.05 megapascals above atmospheric pressure?
Oh yeah, that would be very noticeable. I mean, that's a 50% increase in pressure. So yeah, you'd be hurting. Any of you guys ever heard of saturation diving? So this pops into my head because because actually, if you do it carefully and slowly, you can live at very high pressures and there aren't any major ill effects, but you have to do it carefully and slowly. So, there are gas pipelines and stuff, mostly in the North Sea, laid down across the ocean, 100 to a couple hundred meters below sea level, below the surface of the ocean. Okay, so these things are way, way underwater, say 150 meters underwater. But they need maintenance and stuff, and they sometimes break and they need to be fixed. How do you perform maintenance on pipelines that are 150 meters below water? You can't send scuba divers down there because when you spend time working at pressure, nitrogen gas enters your blood at like a higher amount of nitrogen gas, and then that you're breathing. And then when you go back up to the surface, that gas expands as the pressure gets lower, and it'll kill you. That's the bends. So to avoid that, you have to come up very slowly. But you have to come up so slowly that if you went down scuba diving, worked for a couple hours, it would take you, I forget how long, but let's say a week coming back up to the surface safely. Okay, so obviously that's not financially feasible, You can't have someone work for 2 hours and pay them for a week, So in the late 60s and early 70s, what people figured out was that you could put somebody in a vessel that you could pressurize, slowly crank the pressure up to what it is going to be 150 meters below, So they're at that pressure. Then you send them down. They get out of the thing. It feels normal. They're just underwater working, Then they get back in the vessel that takes them back up. It's all pressurized. So they come back to the surface, and then they sleep, eat, do everything on the surface of the boat, but still in this steel container that's pressurized to 150 meters below. Okay, so they're at this super high pressure, and they do that day after day for like a month. They live on the surface of the water in the ship, but they live inside a pressurized thing, and they never return to regular atmospheric pressure. And then when the month is over, then they very, very slowly, over several days, return to atmospheric pressure in this controlled environment. And then once this thing is at atmospheric pressure, they can pop open the hatch and come out.
Ideally.
And now it's pretty safe, but at the beginning, there were some very bad accidents. And the most famous one, they thought they had, so you get inside like a intermediate area, and then you close a hatch, and then you open the other hatch, so that you can control the pressures. But somebody, I think it was, they were delivering them food, because you have to do that whenever but they went to like open the inner hatch, and the outer hatch wasn't sealed. They thought it was, and it wasn't. And so instantly, the inside of the pressurized tank went from 150 meters of water of pressure to atmospheric pressure. And I mean, everybody was not only killed instantly, but their bodies were unrecognizable as bodies. Like their blood instantly boiled because of all the gas that was liquid that suddenly became gas. And the one person who was at the hatch getting his food, apparently, like, okay, I don't want to get too graphic, but it was really bad.
It wasn't fun.
It wasn't fun for the people who lived. It wasn't anything for the people who died. I mean, it happened in a tiny, tiny fraction of a second,
It shows like the strength of
Exactly.
Like it just shows how powerful it is.
Yeah, exactly. Okay. What were we talking about?
And underwater welding is like the most dangerous job, right?
Well, I think mainly just because of the pressure aspects of, I think that's why. I mean, but yes, it's very dangerous, but it's a lot less dangerous than it used to be. And then there's weird stuff like it seems to basically work, like, and people don't have ill effects, but they seem to have weird joint problems as they get older, and sometimes they develop some weird uh, sort of memory problems and stuff. And I don't know. I mean, it's related to the pressure, but I don't think people are totally clear why exactly. Um, but yeah, it's super dangerous because I mean, if anything goes wrong, I mean, every every part of this chain of events has to work in perfect combination. And if you know, um, if you lose communication or um, lose the ability to control the temperature in there, I mean, like, what do you think happens to the temperature if you're uh, so you're in this vessel and they're cranking the temperature up inside? If they're not also cooling it down, I mean, we know from the way heat engines work, the temperature is going to go up just due to forcing more air in there. And so, other accidents where people have been killed or almost killed have just been from losing thermal control of this thing and the people, you know. So, okay, that's enough about saturation diving, but find out more at your local library. What are we on? C. If the pressure would remain constant over this temperature range, what can you say about the relationship between its internal energy and the change in enthalpy? Okay, well, we can see this from this equation here. So we know that the change in specific enthalpy is equal to the change in specific internal energy plus the change in PV. V is already constant because it's incompressible. Now we're saying that this is also constant. And that means that this goes to 0. And so delta H and delta U are the same. Okay, so number 2. Liquid water, so we can treat it as incompressible. Starting temperature is given. It increases until saturation. The pressure remains constant at 2.1 bar. Okay, so anytime it says tables, you can use the website. So it starts at 100 and it increases until saturation. So it starts at 100 and then increases until it's at its boiling temperature. 100 Celsius, we're used to that being the boiling temperature of water. So why isn't it the boiling temperature of water in this case? Yeah.
Because the pressure is 2.1 bar.
Yeah, because the pressure is like about twice atmospheric pressure. And so that makes the boiling temperature go higher. Okay, so specific heat of liquid water. This one, well, this one you have to get in the table. So let's find this. So we can go to complete property tables. And we want to look for the specific heat of water. Okay, gases, properties of common liquid. So I think we want table A3. Okay, so that's A2. A3. So we want water. And this is at a temperature. Okay, at water it gives the specific heats at a few different temperatures. We want it at 100 degrees Celsius. You can see that it varies a little bit. It's sort of in a kind of symmetric, like parabolic shape, but it doesn't vary much by percentage. But we want it at 100 degrees Celsius. So that's 4.22. And these units are in kilojoules per kilogram. So we want it just in joules, which means I'm going to use 4220.
It doesn't matter that it's a different atmospheric pressure that.
No, it does not matter. It really only varies with temperature. So 4220, and this is in joules per kilogram Kelvin. Now we need to figure out the water temperature at saturation. So here's where I'm going to use the website. So we want water and international units. And we are given that, so we know that the pressure is, what was it, 2.1 bar? So that is 210 kilopascals. Yeah, 2.1 bar. And then for our second condition, we're going to be at, so we want saturated water. So I'm going to, saturated liquid water, so I'm going to put a quality of 0, calculate the properties, and the temperature is 121.8 degrees Celsius. Any questions about that? So this saturation temperature is 121.8 degrees Celsius. Now we want to use incompressibility to calculate the change in H. Okay, well, I'm going to look up the specific volume because we're going to need that. So that is 0.001062. So the specific volume at this temperature is 0.001062. This is in meters cubed per kilogram. How does that compare to the specific volume at room temperature of water? Yeah, very little difference. So at room temperature, it's 0.001. Okay, 1 times 10 to the minus third. So right in that same ballpark. So now I can calculate, I know that C is equal to du dt. And so C is 4220. So 4220 d temperature is equal to d little u. I can integrate both of those from state 1 to state 2. So that's 4220 times the temperature evaluated from, it starts at 100 degrees Celsius and goes to 121.8. And then that's equal to U evaluated from U1 to U2, which is just delta little u. So 4220 times 121.8 minus 100 is equal to delta u. And that is 91,996 joules per kilogram. And now I can use the relationship that says, so the pressure remains constant. We just answered this as part C of the first question. The change in specific enthalpy is equal to the change in specific internal energy plus the change in pressure times volume. This part is 0 for an incompressible material at constant volume. At constant pressure. And so the change in specific enthalpy is also 91,996. And that's part C. Okay, what's the heat added to the water during this process? So anyone have a thought about the approach here? Well, we know some stuff about energy. We're trying to find something about heat that should trigger first law of thermodynamics in your head. So
We know the specific change in internal energy. We just use the change of internal energy to help find the change in.
yes, exactly. Yep. So the change in internal energy is equal to the mass times the change in specific internal energy. In this case, we have 10 kilograms. So this is 919,960 joules. And then the first law says the change in internal energy, we're assuming kinetic and potential effects are small. This is equal to Q minus W. Are there any hints about W? Well, yes, there are. I was hoping, at first I was thinking like, well, if it says something about a fixed tank or something, then we know that the work is 0. Well, this can't be a fixed tank because the pressure is held constant. But we know the specific volume at the start and end. So specific volume. Okay, so I'm gonna look this up again. At the start, at instant 1, we know that the temperature is 100 degrees Celsius. The pressure is 2.1 bar. And so the specific volume so 210, our temperature is 100. So the specific volume is 0.001043. Oh, well, okay. This is a liquid. So we're going to assume that the specific volume is constant. So we could use the temperature changes to find that small effect. But let's instead just say this is a liquid. Okay, so let me erase this. We're assuming incompressible. So the volume is constant, the specific volume is constant. So the extensive volume is also constant. And so the work of expansion, which is this, is equal to 0 because those two volumes are the same. Okay, so this goes to 0.
So that would mean the change in internal energy is equal to the change in heat.
That's right. So all of the change in internal energy is produced by adding heat. So I guess the one thing we have left to do here is the change in internal energy. We didn't calculate that yet, did we? Oh yeah, just up here above is equal to 919, 960, and that's equal to Q. And this is joules. The pressure isn't constant, but the volume is the pressure is constant. Okay, so the pressure would be constant, like if you just do it in if you do this process in an open room or something, So
why did we assume that it's constant?
It was given. The pressure remains constant at 2.1 bar. I mean, all this stuff is what makes these problems hard. Like you know a million relationships and you're just trying to get used to like thinking your way around which ones help you, which ones, these kind of problems just aren't as clean to think about as like for the people taking statics right now, we're how far into the class we've learned 2 equations, and so you just have to learn how to apply them. This is like, a million relationships. How can you find the one that gets you where you want to go with the assumptions you're making? Okay, number 3, are we going to finish this? I'll talk extra fast.
That's number 3.
God dang it. Oh my God. Okay. 5 kilograms of liquid water starts at 1 bar and a given temperature. You add a bunch of heat. Look up the specific heat of a liquid around 40 Celsius in the tables. Okay. We want the internal energy and the change in temperature. Okay. This is pretty similar to the other two. So this is water at 40 degrees Celsius. So we have to go back to the table that'll tell us that specific heat. Like I said, you can pretty much always just use the same one. They don't vary very much. But tables.
And then we do because it has 25 and it has 50.
Yeah, so let's just see what they have. Right, so it's going to be like right in between those two. Yes, exactly. So water, 25 and 50, they're both 4.18. So okay, so C is equal to 4180 in SI units. For B, so for an incompressible material, we were just reminded of this. The work of expansion is equal to 0 because that volume doesn't change. So we have the change in internal energy is equal to Q minus W, and that W is 0. That Q is given as 100,000 joules. And so that's the change in internal energy. And now we know that 4180 is equal to du d temperature. And so 4180 d temperature is equal to d little u. Integrate both of these. Both of them are going from state 1 to state 2. Okay, so now this one is 4180 T from the starting temperature of 40 Celsius. And we're going to a T2 that we're trying to find. This one is, now you have to be a little careful. This is going from U1 to U2, which is delta little u. But we don't know delta little u yet. We know delta big U. So delta little u is equal to delta big U divided by the mass. The mass is 5. So this is 100,000 divided by 5. So 20,000. And now we can put these into this equation, and we get that 4180 times T2 minus 40 is equal to 20,000. And so T2 is equal to 44.78 degrees Celsius. Any questions about that? Okay, we're over. I'll have your test back on Friday.